Hi, this is Mark Graban. Welcome to some extra bonus material. I apologize for trying to cram in more than 45 minutes worth of material into a 45-minute webinar, but here is an opportunity to share some of that with you in this recording. If you didn't see the full original webinar, you can find that in the webinar library and in our YouTube channel, How to Use Process Behavior Charts to Improve Case Studies. And again, here's some of that bonus material. So in the other webinar, I made up this fake bad game show called Is It a Signal? Trying to figure out if a change in a metric is noise or if it's a signal. And in that other webinar, I shared different use cases and examples of using a process behavior chart for time series data, a metric that is changing over time. But we can also use process behavior charts to take a snapshot in time, kind of slice differently, and doing a static comparison of individuals, teams, departments, organizations, to look and see if the differences between those individuals or groups we're comparing, if those differences are the equivalent of noise or just within the realm of routine variation, or if there's a signal that one or some of these organizations or individuals are significantly different than others. So one data set, and as I did in the other webinar, it's sometimes helpful or it's just easier to share public data sets. Somebody who has knowledge of the U.S. Veterans Administration, the Veterans Healthcare Administration, pointed me to a website that has a lot of data and metrics for the different VA hospitals in the United States. So it's a program called SAIL, Strategic Analytics for Improvement in Learning. And I love the name of that. I think metrics should be used for improvement in learning. Far too often, metrics are used to judge or punish or reward. And unfortunately, we end up often rewarding randomness instead of rewarding significantly different behavior. But here's an example. This is a spreadsheet that you can download from the SAIL website. I chose the Detroit VA. I grew up outside of Detroit, so it was just kind of a random choice. And you see all kinds of different metrics. And I just picked the one on the top here. It's a metric called the Acute Care Standardized Mortality Ratio. I'm not an expert in that methodology or in that ratio, but there's a number. And that number for Detroit in Q3 of 2018 was 0.891. And they make it difficult. You've got to download a different spreadsheet for each quarter. I cobbled these together into a spreadsheet, and it created a process behavior chart. They had data available going back just to Q3 2016. So we've got the data with the blue line, we've got the average with the green line, and we say, oh, well, the metric is above average some quarters, below average some quarters. We've got the lower and upper natural process limits. And because we don't have any evidence of signals, we don't have any data points outside the limits or any signals from our other rules, we could I would suggest that we would say this is all noise, that the differences between any of these months are not statistically significant. They're not worth explaining. It's not worth getting too excited or too upset about. Now, instead of this reactive mode of saying, well, what went wrong last quarter? I've always talked about how we need to improve the system. So if we want to reduce the average that the standard mortality ratio is fluctuating around, we can do things to improve the system, but that requires stepping back, taking a systematic approach like using A3 problem solving instead of this real reactive kind of approach. So we've got this noise. Here's the data where I think, a chart like this it gives us context of how Detroit is behaving. But that spreadsheet also says, well, Detroit is worse than the best 10%. And then they repeat the best 10%. We've got the 10th percentile, the 50th percentile, the 90th percentile. So we'd say Detroit nationally is doing worse than the 50th percentile in that quarter. So remember that spreadsheet, that's just a snapshot in time. So we want to look at how if we care how Detroit's doing against the 50th percentile. I think it's interesting to see that. So we've got the Detroit performance in orange. The 50th percentile nationally is in blue. So I think, for one, it's interesting to see that the 50th percentile fluctuates. And Detroit's performance is fluctuating. And here, look at this. We have 9 quarters. We have 3 quarters where Detroit was better than the 50th percentile. Maybe average isn't technically correct, but better than the middle. We had 3 quarters where it was exactly average, 50th percentile, and we had 3 quarters where it was worse. So if we say, well, how is Detroit doing compared to the VA nationally? The question might be, I don't know, or it depends. So this is where we can use process behavior charts to compare organizations at a point in time. So there's a region in the VA, and there was one hospital, I forget what city it was, it didn't have data available. So I took the other cities, ranging from Ann Arbor, Michigan to Saginaw, Michigan, and there's some other states represented. So here are the numbers for Q3 2018. Some numbers are bigger than others. Well, what conclusions would we draw? We look and say, well, Battle Creek has about half the standardized mortality ratio as Fort Wayne. Does that mean we should send all of our patients to Battle Creek if they have the capacity? Does that mean Battle Creek is doing significantly better? So we can answer that by drawing a different form of process behavior chart, where instead of taking Detroit quarter by quarter, we're laying out all of these different cities from left to right in the process behavior chart. And we calculate the lower and upper limits. We calculate the average. We use basically the same spreadsheet and the same methodology that we would use for a time series process behavior chart. But one of the keys here is that we have to put the cities in some random order, not ranked low to high or high to low. Alphabetical order is as good as any order. So we draw the chart and we use just our first rule. We're looking for any data points that are above or below the limits. We don't see any. I would conclude that the differences in the Q3 2018 ratio between these different cities, they're all within the realm of fluctuation. And I bet I'll do a blog post about this. If I were to run the same analysis for a different quarter, I'd be curious to see where different cities rank and how they stack up. But if we were to choose arbitrary rules like, punishing those that are performing 20% worse than average, or performing in the lower decile of this region, or arbitrary rules like that, we may end up punishing randomness. And I don't think that's a good basis for management. So we can also look at, there's a different data set out there through ProPublica, which is a nonprofit investigative journalism organization. They were looking at surgeon performance within a hospital, across different hospitals. And one thing they were looking at was complication rates for the data set I chose to look at was knee replacement surgery. So this is a snapshot of all of the surgeons at a hospital. This time I chose the Dallas-Fort Worth area. I just picked a hospital. So you can see they've got these green, yellow, red zones, and they're ranking and implying that, well, it looks like 2 doctors are bad outliers. They're in this red performance zone. And off the top of my head, I don't know how arbitrary the green, yellow, red boundaries were. So we've got a bunch of doctors in the yellow range. We've got some in the red. So I would still ask that same question of, well, statistically, given the variation that's going to be in the system that they're working in, is that a statistically significant difference? So here they look at the complication rate. And now I think it's interesting. They're showing a confidence interval, because ProPublica only has access to Medicare, Medicaid data. They don't have data from private payers. So they're estimating the surgeon's complication rate. So this is, I think in a way, this is good statistical thinking, to think about any number in terms of, well, there's going to be a range and a confidence interval. It's like political polling. If somebody is at in a election race and they're polling at 52%, well, there's always this margin of error. So their opponent might be at 48% if it's a 2-person race. But then you've got this plus minus margin of error. It might be plus or minus 3%. So that's essentially a dead heat. 52% could actually be 49%. And the candidate that appears to be polling better might actually be doing worse, because you've got that kind of gray area fudge factor of a confidence interval. And so, here they've got an adjusted complication rate. There's a methodology for trying to make apples to apples comparisons based on different factors about the patients. So we can compare surgeons in a hospital at a point of time. And so I've taken real data. I've just masked names and given them random letter names. So we've got complication rates of 1.9%, 2%, 3.4%. Should you always stay away from Dr. D, who's got a 3.6% complication rate? And I'm sure not all complications are the same. And so there's that question too. But we draw a process behavior chart, and we see basically the range. Well, again, we see some doctors are above average, some are below average. Doesn't tell us a whole lot. That's not surprising. But we calculate the lower and upper limits, and we say, well, basically any performance between about 0 and 4.5% complication rate is within the boundaries, the range of noise, that we shouldn't fire doctors with a 3.5% complication rate. They are not statistically significantly different in their performance than the other doctors, and they're all working within the same system. Same ORs, probably the same equipment, the same sterilization department, instrument sterilization. They're part of a system. Now we can compare, on the right, here's a chart for Hospital A. Hospital B in the Dallas-Fort Worth area has roughly the same average complication rate. And we look at their doctors going A through J. We've got one doctor who is kind of a near signal. There's less variation from doctor to doctor. So the limits for Hospital B are calculated, they're narrower than Hospital A. And some of those limits will, and I'll show an example of this in a minute, will vary a bit based on the random order of doctor to doctor. But so that's where, this methodology is a little bit less precise than the time series process behavior chart. But I think it's useful. And we can step back and ask, how much are we overreacting to noise in our comparison between individuals or hospitals? We love ranking, judging, evaluating. I'd be interested to apply this methodology to pay for performance data. Are we rewarding some doctors and punishing others when perhaps their performance is within the realm of noise or insignificant difference in performance? Or look at another example. I love looking at sports data. And if we look at, I just poked around at a couple of different metrics, and I thought this one was interesting. The number of home runs hit by each Major League Baseball team. So we had the 2018 season that ended a couple of months ago. We take a random ordering of teams, and again, I think alphabetical order of the 30 Major League Baseball teams is as good of order as any. And we plot this, we calculate an average, we calculate lower and upper limits. The team that hit the most home runs last year was the New York Yankees. They hit 266 home runs or so. There's a big difference between them and the Miami Marlins. The Miami Marlins hit, I think, about 120 home runs. But each of these teams are within the realm of noise. And it's not to say that next year randomly the Yankees are only going to hit 120 home runs. The Yankees are still going to be good. The Red Sox are still going to be good. But we look at the chart here, and the Yankees were better last year. But are they historically an outlier? Well, not really. They're within the realm of variation for teams in baseball last year. If you go back, though, and look at the New York Yankees in 1927, and yes, I'm cherry picking the year for those of you who know baseball, here is that chart for 1927, and I've made the y-axis the same. Now, the New York Yankees in 1927 were an outlier. So I would look at this and say this was a historically great and unusual season. The New York Giants, now the San Francisco Giants, hit the second most home runs. They were within that realm of kind of the noise of how many home runs teams hit that year. I think it's interesting to see how the game has changed. The New York Yankees would have been a below average home run team in 2018. But here we have a signal. In 2018, we had some teams that were good. In 1927, we had a team that was historically uniquely good or outstanding. Maybe have a Hall of Fame team and a Hall of Fame season. So when we have a signal, it would be worth asking why. Well, that why, a big part of it was Babe Ruth, a historically great player who at that point hit more home runs than anybody in baseball history. He held the record of 60 home runs. He hit more home runs than most teams hit in 1927. That's how much of an outlier his season was. So if we look at, again, this 1927 season, here's the first chart I drew. And then if we randomize the order of teams in different ways, it tells basically the same story. I mean, there's one version of the chart where the Yankees are almost a signal. So that's part of the kind of imperfect precision involved in using a process behavior chart this way. But I think you can pay attention to near signals as standing out. The thing you don't want to do is rank all of the teams from low to high, increasing, or high to low, decreasing, because that makes the differences between teams smaller and less random, and then you get narrower limits, and you get a bunch of teams that are outliers. The ordering of who and what you're comparing has got to be done in a random way. So I'm going to actually do two separate bonus videos. So this first bonus video was about using process behavior charts for comparison in a snapshot at time. I'm also going to do a separate bonus video about looking at process behavior charts when a time series is not fluctuating around an average that's flat and horizontal, but what happens when you are kind of increasing linearly and you're looking at noise and variation around that linear trend. So that's the other video. We'll have it on the webinar archive page. It's going to be in our YouTube channel. I'll put a link on screen, and I hope you'll check that out. So again, if you'd like to learn more about KaiNexus, go to KaiNexus.com. If you'd like to learn more about my book, Measures of Success, you can go to www.measuresofsuccessbook.com. And I've also blogged about some of these topics. If you go to leanblog.org, search for process behavior chart comparison, or search for Babe Ruth or something like that, you'll find different links to posts on this theme. So thank you for checking out this bonus content.